soils, and especially the axial behavior is what is very interesting for this problem. So pile groups in liquefiable soils, uh, there are many different issues with them. Yeah. Uh, for example, it if my pile cap is above the ground surface or resting on the ground, or whether it is embedded, that will make a difference. The amount of embedment also makes a difference. Spacing of the piles makes a difference, and all the depending on the spacing, you can get whether the whole pile group will rotate or it can bend. So is it the flexural stiffness that is important or global rotation that is important? So all these things change depending on spacing of the piles. So camp embedment, pile spacing, tip embedment, and pile stiffness. Before I get into this, I want to kind of take you through a thought experiment. Suppose I got a pile cap and say 2 by 2 pile group. Initially, before when we constructed that, when there's no liquefaction or no earthquake, what do we expect? We'll have some end bearing, we'll have some shaft friction, and that is keeping the vertical load in equilibrium, right? So this big downward arrow needs to be balanced by these two and integrated values of the shear stress on all the 4 piles. During the shaking, liquefaction happens, pore pressures rise, and we know the effective stress comes down, and you'll get loss of capacities. You lose bit of your end bearing, your shaft friction probably disappears fully, and that will give rise to settlements. But what we don't know is who's keeping the thing in equilibrium, right? So we know that is a external load that is always going to be there. So somebody needs to oppose that, but we don't know who is doing that. So that's why it's a question mark. After the earthquake is finished and the soil consolidates, we more or less recover what we had here, right? So this one, pre-earthquake and post-earthquake, you will regain some level of pile cap bearing capacity. You got the shaft friction back, you got the end bearing back. Yeah. Oh, earlier I forgot to mention you also will have some level of cap bearing, which in most designs, normally the designer will ignore the pile cap capacity and they'll say that is conservative. Okay, so if I ignore that, otherwise what you have to do is to take the pile cap area, subtract the areas of the piles themselves, and work out your normal shallow bearing capacity factor, and say that is going to be addition. And the reason people are not so sure about that is how much load that carries depends on the stiffness of the piles, how much end bearing, how much settlement I got. It's not obvious that all these will be mobilized to the same level. So although my bearing capacity here may be high, I may not mobilize all of it because most of it is being taken by these. Okay, so we know before, we know after, we think, but during the liquefaction event, we don't know. So I had a student called Mark Stringer, who is now a senior lecturer at Christchurch University in New Zealand. And Mark was a game. He used to work for BP, and he got tired of sitting alone on the offshore jackup rigs, and he said, "I want to come back and do PhD." I said, "Yeah, I have this idea. Do you want to try and do research on this?" So he created this pile group. So the pile groups were The base had a pore pressure transducer in here. We had gauges all along, but these strain gauges are designed to measure axial loads. They are not meant to measure bending. So we had axial load measurement at 5 locations, and we also had some loads, total load cells on the top. We of course monitor the acceleration of the pile cap and the pile tip and the settlement of the whole pile group. So the first set of experiments he has done is he inserted, so our soil profile is loose sand and dense sand, loose sand overlying dense sand. And this is very realistic because you'll never design these piles to end up in just the loose sand. That is asking for trouble, right? You will always embed them to certain depth. Normally you work out the effective length you need by using, I think, Bond has one equation, Fleming has another equation that tells you how deep I should go, maybe 5 diameters, pile diameters or 8 pile diameters into the dense sand. Yeah, so we followed those rules and installed them to that depth. And here are all the load cells, effectively load cells. They're strain gauges, but they're measuring axial load. And S1 and S2 are the wire gauges to measure the settlement. A7 is the accelerations. We measure always the pore pressures and accelerations on either side. Very straightforward. The first set of experiments had the pile cap clear off. So this is my ground level and I have a gap. Normally onshore you don't do that kind of thing. The pile cap is either on the surface or even embedded into the ground surface. Offshore, many times you leave the pile cap a little bit free because you may not be able to drive the piles to the depth you want it. So it is not totally made up. It is possible, especially offshore, to have situation like this. We wanted to try that and compare with when the pile cap is sitting on the ground. So those are this I call freestanding, means pile cap is clear of the ground surface. This was all with the before we had the servo hydraulic shaker, so we did all this work using the SAM actuator, which I showed you in the previous lecture. So it creates nice sine waves, right? So it created a sine wave like this. Lots of deliberately we had quite a lot of cycles in this, and these are the loads at the top of the top and bottom of the piles. So SGA-A and SGA-E. And you can see that they're getting up in prototype scale about 500 kilonewtons there, and here it is a bit less than 500. So the difference between those two should tell me how much is my shaft friction, the shaft capacity. Okay. Before we get and look at the shaft capacities, we also are interested in how is the load being generated. Pile loads are seeing increasing load as the pore pressure dissipates, right? So we had so here the cyclic bit is removed and we are only looking at fairly long term. Yeah, these are like 4,000 seconds or something, and you can see the green is a lot bigger than the blue, and blue is at the bottom. Yeah, I think so. Let's go back and check that. Oh, I haven't marked on here. Yeah, I'm pretty sure the one is at the top and one is at the bottom. And as the pore pressure is dissipating post-earthquake, we can see these loads are peaking. Yeah. We can also convert this into the QE, the end bearing and the shaft capacities directly, because we know the area of the pile. So clearly during shaking, we lose shaft friction, and as you dissipate the pore pressure, is the shaft friction coming back or not is the thing we are looking at here. Another thing that is important here is the settlement. And here I'm showing you data from two different shakes. Earthquake 1, where I got a massive amount of settlement, nearly 1,000, it's almost a meter and a bit. And the second earthquake, similar size, but second time round, the soil doesn't liquefy as much, and also the pile cap has settled a lot, so it may have come into contact with the ground, right? But what I'd like to see is, this is much steeper than this, right? So we had an idea on, suppose instead of stopping the earthquake 1 here, if we continued, what would happen? It would probably have this earthquake 2 is basically that, isn't it? We stopped and applied a second earthquake. How is the settlement going to continue? So I need to stack these one after the other. And this is what happens. This is really beautiful. I hope I'll go through it, and earthquake 1, the settlement stopped here. And if I put the settlement I got in the earthquake 2, it's almost continuing the same thing. There's no field data, no real data like this. And this is one of the nice things about the centrifuge testing. It seems that the settlement curve is a unique curve. And soil remembers what damage you have done last earthquake, and then in the next earthquake it starts from that damaged state and continues. We may have forgotten that there's a previous earthquake, but the soil remembers. This is almost like in consolidation and so on, you say stress history is important, right? Whatever the stress history you subjected to the soil before, it remembers it. And it's true here as well. So it's when Mark plotted this, I couldn't believe my eyes. It is so continuous, the function of settlement. It really stacks well. And after that, he has done on a third earthquake, fourth earthquake. They also stack up as a continuation of that. I'm not showing you that, but basically that is quite a revealing point from soil mechanics point of view. If you ask the structures guys, what they'll say, settlement is settlement. By the time you got 1.5 meter of settlement, the pile is dead, the structure is dead. This is not interesting for us. But for geotech people, this is interesting because that tells you something very fundamental about the soil. Yeah. So in successive earthquakes, it remembers. Okay, we've done all that. So we then tried another same pile group in same soil stratigraphy, loose sand overlying dense sand. Instrumentation location is the same. Only difference is this time the pile cap is in contact with the ground, right? That's the only difference. Now I'm going to compare what you get from the freestanding pile and the pile cap in contact. These are the two cases we were looking at. Pretty much similar level of acceleration. In most liquefaction problems, input motion is actually not that important. Once you hit it anything above 0.1 g, the soil will liquefy. And whether you do like nice swaras in music, right, or sing different ragas, the soil doesn't really care. It only needs that 0.1 g as a threshold acceleration. After that, it liquefies. You can apply Kobe motions. For liquefaction problems, the input motion shape is not that important. Okay? For dynamic problems it is, but for liquefaction it isn't, because the soil liquefies and the structure does what it does. When the pile, in the freestanding pile, I'm starting at about 400 kilonewtons before the earthquake. Then it changes, yeah, and after the earthquake, I'm ending up with slightly lower values. Same at the top of the pile as well as tip of the pile. When the pile cap is in contact, it starts with pretty much the same numbers and it is dropping all the way to zero in both at the top of the pile and at the bottom of the pile, and then it tries to recover. And this completely blew the mind of Mark, and when he explained this to me, my brain also went on a bit of a fire. What the hell is going on? Why are they so different? The only difference is whether the pile cap is freestanding or resting on the ground. The loads are totally different. And worse than that, these are coming down to zero. This means that the pile is not doing anything. And we said, whoa, this is not what we expected at all, right? So, these are at the top and bottom of the pile, but we also have data for different locations within the pile. And that's what I'm plotting here. So, we got at 5 or 6 different locations our axial load measurements using strain gauges. So for a freestanding pile, before the earthquake I start with 1, yeah, and during the earthquake it drops to 2, and then after the earthquake it recovers 3, 4, 5. So 5 is the residual load. So if I look at this, the smallest value it is falling to is about, let's say, 200 kilonewtons. Yeah? When the pile cap is in contact, starts at 1, comes all the way to 2, 3, 4, 5 is the recovery times. This is the post-earthquake reconsolidation. And these values are pretty close to 0. I said, what's going on here? Basically, this is the same data as what we have seen before, except now we are plotting the loads along the length of the pile. Yeah? And then the penny has dropped in our head. Basically, if my pile cap is not in contact with ground during this particular earthquake, the total load on the being applied on the pile cap, somebody has to carry it, right? So this I can only come down to 200 because that load has to be carried through all the elevations of the pile. Whereas when the pile cap is in contact, the piles completely don't carry any load. So who's carrying the load? The pile cap, right? So whether the pile cap is free or in contact makes all the difference on the load the pile is going to see. So from equilibrium consideration, this is right, because somebody has to support the load. Whereas here I got the pile cap to carry all the load, so the piles are completely unloaded during the
It's one really good construction pattern. Pile cap should be made of
okay. This is why I was showing about this settlement, right? So if I have my freestanding pile, yeah, freestanding pile group where the cap is away, yes, the piles are carrying 200 kilonewtons in liquefied soil, right? which means that they will mobilize a lot of settlement. That's the only way it can generate enough resistance to support the load. Whereas the other one, the settlements will be a lot less. And this is quite a revealing set of experiments. So here the settlement will be less, but you are basically relying on pile cap. So what routinely designers are ignoring is what is saving them when this ground liquefies. And there are many examples where routinely, if you have liquefiable soil, you drive piles to go into dense sand below. Even Delhi, Akshardham temple had piles like this. So many examples I can give. So when the earthquake happens, it's the bit they ignored in their design is what is going to save them, which is a bit scary. Because as a designer, you are saying, this is not going to be important for me, and I'm going to ignore the pile cap capacity. And that is the bit that is actually holding your structure up when the cap is in contact. Otherwise, if it's freestanding, you'll get a lot more settlement. Like 1.5 meters, by which if I got 1.5 meter settlement of pile, my structure is more or less died by that amount of settlement. Yeah.
But what if it is a reverse case? Like it is pile cap resting on the soil. After first earthquake, the soil is going to sink.
Yeah. And along with the pile.
Not along with the only like because like the pile is operated in the rock.
In the rock. Then, as I said yesterday, the problem that now becomes a buckling problem. If you, this is the problem with soil, right? In English, there is what is called Murphy's law. This is not real law. Murphy is an Irish guy, and they have a really positive outlook on life. Murphy's law states that if something can go wrong, it will go wrong. I mean, it was obviously a joke that Irish people, it rains 300 days in Ireland out of 365 days. So they are very gloomy. It's always raining and drizzling. So they feel life is always on the down. So this is why the joke is that the Murphy came up with this law saying if something can go wrong, it will go wrong. Okay? So same with these piles. If you rock socket them, they'll try and find the way they can fail. That would be by buckling. If they're freestanding, they will fail by settling. Yeah. If they're sitting on the pile cap is resting on the ground, as long as the pile cap is large enough to mobilize enough capacity, it will not allow so much settlement. But say I made my pile cap quite small compared to say I got 2x2 or 3x3 pile cap, right? 3x3 piles with a cap. And say I got only a tiny amount of net area, then I can't get enough capacity. Then also it will settle, right? So whatever can go wrong will go wrong. That's why I'm quoting the Murphy's law. It's basically the soil is not wedded for one failure mechanism or the other. Whatever is easiest, it will do. And that is the point of these. Okay? So when this PhD work was done, my colleague and famous professor Malcolm Bolton, he coined this phrase, now you see, now you don't. Okay? Initially you see the piles. During liquefaction, piles disappear, and post-consolidation they reappear when the pile cap is sitting on the ground. So this is, have you seen What is that film? Not Catch Me If You Can. They rob the bank and all that kind of stuff. Anyhow, there's a film where now you see and now you don't. So he applied that to this pile foundation and it kind of stuck with us. So this is really where centrifuge testing can reveal the load carrying ability of piles and how the load is getting transferred to the soil. If you now I know this is what's going on, I can design. All I need to do is to make sure that pile cap has enough capacity, right? So maybe make the pile cap half a meter bigger in every direction. I'll have enough capacity. Okay? So these, although we start these experiments for fun, more or less, and let's see what's going on, once you get the data and look at it carefully, and as I said, we went through quite a lot of thinking to go with this. There is also a case where the early version of this data we presented at a conference in Greece, and there was this Japanese guy in the audience, and all he got stuck on was no pile caps, the pile settling 1.2 meters unacceptable, and he stood up and walked out of the audience. And my student who was presenting this got very angry, and he said, "This 1.2 meter settlement is not. You're obviously not going to design a real pile group to have that kind of settlement. But when you're doing experiments, you can design them to fail, right?" But the Japanese guy didn't quite understand what my student was trying to say. Yes, we also know 1.2 meter settlement is too much. But the reason we design the experiment like that is to get big settlements so that you can clarify the mechanism. So it's not, you don't design experiments always to be not failing and be safe. Sometimes you design the experiment to fail because there's a lot, it doesn't cost us anything, right? There's no building, nobody's getting killed. Yes, the piles settle more, so what? We measure how much they settle and then we understand what's going on. Now we understand what's going on, anybody can design much better. And that's the point. Anyhow. Okay, any questions on the axial capacity? Did you guys find that interesting or not? Very little work is there on axial load carrying capacity of piles in liquefiable soils, by the way. Even my book, this work happened after I wrote my book, so it's not in that book. There's a new book Kenya has published, Amir Kenya has wrote, and I contributed a chapter for that, and we included this in that, this work there, and also published in Canadian Geotechnical Journal. So it's out there, but you need to look for it. Any questions? Pure horizontal. Yeah. Making it incline and all that will make it a lot more complicated. And that's the bit I'm going to talk next. This is after the Christchurch earthquake, and I had a student called Jenny Haskell who looked at lateral spreading, which I'll talk about now. What I want to convey is the excitement of research more than anything else. This is how you can go about, and these are all, we're not doing research for fun. These are real problems and they have real consequences. Yeah.
Sir, actually, it's like normally, like, once it is reaching critical state, sorry, the volume remains the same.
Beyond critical state, yeah.
While driving itself, only like if you are going into like adding more vibrations, so soil will be settled.
Not necessarily. When you do pile driving, what you expect is at the base of the pile or the pile tip, that soil would have reached the critical state, right? In driving, because you have to fail the soil to get the pile in. Yeah? But there are other things that go around, like, for example, Dave White, we were talking about him earlier. One of the things his PhD was on driving a pile, leaving it for some time, and trying to do a pile load test on it. And what he observed was that the pile load capacity goes up if you leave it for a certain amount of time. And this is normally called pile set or something like that. But is this the real question in soil mechanics is that just dissipation of pore pressure, and therefore you generate some pore pressure when you drive the pile, and if you allow enough time the pore pressure dissipates, my effective stress recovers, and therefore I can get extra capacity. Is it just that, or is it the fabric of the soil which got disturbed when you're driving the pile? The grains can reorganize and generate some level of fabric. Now, like always in research, there are people like Dave White who will sit there and say it's all pore pressure because he comes from Cambridge School, and we believe that is true. And there are people who do fabric like Mazid Mansari and other people who always say everything in soil is due to fabric change. I don't think we are 100% right. I don't think they are 100% right. The truth is somewhere in between. There is some fabric remolding happening. There's definitely pore pressure dissipation going on. And the set you get is a combination of the two. Okay. So again, research never finishes, right? So somebody can design experiments specifically for that and see, especially if you have carbonate sands, which will crush when you drive the pile, and that's why you get pile runs as well in those type of soils. Then is it the fabric, is it the pore pressure? Would be a real interesting research project. Okay? Yeah.
This is the behavior when the pipe cap is resting on ground and we are not considering the pipe cap capacity in the design.
Yeah, normally that is, I mean, you can talk to many designers, they will ignore it.
Also, like in pile raft design, we include the capacity of that raft in that behavior will be the same.
No, pile caps are much smaller, and usually you are only using them for maybe 3x3 or 2x3, that type of pile arrangement, right? To go under the column. Pile raft is a different beast. Pile raft is, you got the raft covering the whole building area and you got piles. The big question there is the load, how much of the load is carried by the piles, and within that how much is end bearing, how much is shaft friction, and how much is carried by the raft. Now, routine design, static design, I also recommend pile raft for many problems, in consultancy problems in Kakinada, for example, where the structural designers who are designing this, they don't understand pile raft foundations. So whenever I say, go do this, they'll say, are you sure? And I say, yeah, I'm pretty sure that's how you do this. The load sharing between the pile cap or the pile raft and the piles is a real interesting one. People like Randolph over years have come up with springs and pile as a spring, the beam on Winkler foundation type of analysis for the raft. And in the end, there should be strain compatibility. Basically, if the raft is going to bend, then the pile also need to get pushed down, and you work on that strain compatibility between the pile and the raft. Again, most of the stuff Mark Randolph has done is to do with imagining all this is elastic. Yeah, we know the soil is not elastic. Therefore, there's a lot more work to be done, even for static, which he had a bunch of students and he did quite a lot of work on that. If I were to look at raft foundation with piles in liquefiable soils, that is going to be even more interesting. This is just a precursor for that. So when I get a next bright PhD student, that is in my mind to go and do that. I haven't done it yet, so I can't answer. But you're right, pile rafts are a different beast, and the load sharing is going to be very interesting. Okay. Okay. So the bit about laterally spreading ground. I'll do the one version of this today, and the rest of it I'll do tomorrow, where we look at the limit equilibrium methods as well. So the problem is piles. Here I'm focusing on pile spacing. Typically, pile spacing is anywhere between 5D to 2.5D. That is the range. You don't normally design 10D spacing. That is almost designing like single piles. 5D is the upper limit. 2.5D spacing is the lower limit. So when Jenny showed up, we thought we'll look at this because as she started her PhD, this Christchurch earthquake happened, and Mishko Kubranowski was interested in this. So cap embedment we dealt with for level grounds. Now we are looking pile spacing. The other ones we will do later. Typically what you expect is that if I have piles and I have a sloping ground coming, trying to spread past the pile. I showed you some field examples from Taiwan earthquake in the last 2 days. You expect passive wedges to form behind the pile, behind the piles. If the spacing is close, these wedges will overlap, right? So the amount of load I'll attract will be less. If the spacing is large, then these wedges are pretty much on their own. So the load I attract on my piles will be big. So that is conventional wisdom. There are also things like if the free field soil is displacing, like with increasing amplitude towards the surface, the soil in between the pile group may move less because most of the load is being carried by the pile, right? So it will flex. Say if it's a flexible pile, it does something like that. But these displacement vectors will be smaller than this. We don't need centrifuge test. We can guess this is what happens. Also, we talked about formation of these hinges. So we do get the peak bending moments will be somewhere like that, which we looked at yesterday. Effectively, the New Zealand code talks about restraining action and driving action. So the earthquake creates the driving action and the structural stiffness provides the restraint. It's like a frame action, right? Basically a pile group with a pile cap is like a frame. Now this is, I probably showed you this already. Typically this is what we are worried about. The excess pore water pressure will, once the earthquake starts, it builds up and stays like that until it starts to dissipate in the post-earthquake period. So I think I showed you this already, this animation, right? So you got initially stiff response, and as the pore pressure builds up, the loops, the tau gamma loops widen up, and as it goes, they become these what they call banana loops, where my tau gamma response is almost like flat, but at extremes I get dilation to create this stiff response. But most of the strain range, you get very soft response. Right. So we wanted to model this in the laminar box. I needed the laminar box because when I shake this, the soil wants to move from upslope to downslope. So if my ends are, even ESB model container ends, while they match the shaking, they can't deform with the soil. So laminar box is required for this kind of lateral spreading problems. So also we mount this, we make the model horizontally and we put on a wedge, either 3-degree slope or 6-degree slope, and you mount them on wedges. This is what we do for other tests as well, which I'm going to talk about tomorrow, NAPETS test, but that's basically. And then you drive the pile. This is obviously the 2D spacing pile. And then you put on the centrifuge and you do the test. And then post-test you can also excavate and see where this ended up. So you got some base layer, which is dense sand, and the liquefiable layer. In this case, our pile cap is always embedded into the soil. Okay? So we are not worried about the settlement issues like what I've shown you earlier. So when I shake at the end of it, it will do that. Okay? So this is an animation she created, but I can show you pictures afterwards. Basically, each of these rings can slide on the next one, which means if the soil wants to go there, this will simply follow it. This is a cool video. This is the plan view, and this is the first time we had high-speed camera. So this camera is taking 1000 frames a second. So although I'm shaking it quite fast, I can still capture and see what happens during the shaking. So that's the plan view. The 4 piles are going in, yeah, and this is sorry. So the slope is high there and down there. So we expect the slope to move in this direction. Yeah. So I hope this plays. Okay, so that is what has happened. So you can now see that this whole pile group started there and moved. I'll replay it again and you can mark the initial position. So it's there, right? And after all the cycles of the earthquake, it has ended up here, right? We can see also the soil that is coming here is being stopped by the piles. So these squares don't deform, whereas these started to shear on the sides of the pile. So just having squares, we can see where the strains are. Okay, then we can look at the data itself. So that is visually good, but what you really want is the look at the data. So this is all in dense sand, so nothing much happens. Yeah. In the loose sand, I'm looking at the pore pressures. You start getting big acceleration. Sorry, my mistake. Input acceleration within the dense sand, nothing happens, but in the loose sand, you get these big spikes. Yeah, and at the surface, the whole amplitude drops off, because if the soil turned into liquid, accelerations cannot go up, which means the top layer will get isolated. But why are these things so big is the question. And that is because of the thing I've shown you this morning. When I'm at zero stress state, if I try to shear the soil, it will have to go along the critical state line, and therefore it has to create a lot of suction. If it creates a lot of suction, the soil temporarily stiffens, and therefore it can pass big acceleration. This phenomena was named by Bruce Cutter and I think a guy called Gudgeon as deliquefaction shocks. It's basically a shock wave going through the soil, because the soil which is like liquefied for a fraction of a second turns into very stiff material, and then it softens again. So whenever it is turning into stiff material, I can carry this shock wave. So the physical data you get actually has a lot of meaning associated, and the same thing happens I'm sure in reality as well. Now we can also take a little time frame in here, like a yellow box, and this yellow box is plotted here. So I'm only seeing few cycles. Then I can, if I draw a vertical line, I can see the delay in the propagation of the shear waves clearly. So that is the phase lag I'm getting as the shear waves go from top to bottom to top. So there's a lot of information you get, which means if I know the delay, I can work out shear wave velocity. If I can work out shear wave velocity, I can work out what the reduced shear modulus is. All that information is coming straight from the accelerometers. Pore pressures. In the dense sand, I get maybe 60 kPa excess pore pressure. But if you work out to liquefy the soil, I need about 80. So this dense sand hasn't quite liquefied. As I go to the top, I can see I'm crossing the liquefaction line. So we know the shallow layers, the slope layers are all liquefied. Now, earlier I said that we are getting this deliquefaction shocks. That is confirmed here because the pore pressure is not just going up. In every cycle, it is dilating, or it wants to dilate, and you get suction. And I can see the suction. So that is, say, 35. I'm getting a suction of about 15-20 kPa. And it's even more there relative to the shallow depth it is. So that's why the soil is locking on us. So we see the acceleration response, but also confirm that with pore pressure response. Okay? So this all fits together. Great. This is what doing experiments is all about. But really, we are trying to answer a design problem, right? So here, the piles are also gauged with strain gauges, so we can measure the bending moment. So I got 5D spacing and 2D spacing. And this is the upslope pile, and that is the downslope pile, right? So basically what we are saying is, and the slope angle is 3 to 6 degrees in different experiments. Okay, so this is my upslope pile, and this is the downslope. So we are looking at the bending moments in these. Yeah. So at the base, obviously the bending moment has to be 0 at the tip of the pile, and we get a shape. If I plot these bending moments at a particular instant, a shape like that. And the downslope one, this is about, let's say, 300 kilonewton meter, and here it is about 500 kilonewton meter. Yeah. So clearly the upslope and downslope are not carrying the same bending moment. When the spacing is reduced, base and also the top are almost 0. And I'm getting a different shape, right? So this one is a double curvature like this, and that is simply one same shape, both for upslope and downslope, and also they're not that different. Why is this? The only thing we changed is the spacing. Yeah? What is it trying to tell us? Sorry? No, pile cap is embedded for both cases. It's only spacing that is different, right? Yes. Yeah, but the 5D spacing means I'll generate individual wedges according to what I said before, right? Actually, it is to do with the mechanism, right? When the spacing is big, if I draw the plan view, the soil is able to flow like that. If the spacing is less, the soil does that. Oh, sorry, I can do that. So if the spacing is less, it's almost working like a one large diameter pipe. Whereas these ones, it can go around the upslope and downslope, the top and bottom piles separately. Which means in one case, the whole pile group will simply rotate. If it does that, the bending moments will be small. If I have more spacing, then the piles will have to bend like that, right? That creates a lot more double curvature and bigger bending moments. Simply by changing spacing, we are changing the failure mechanism. So closely spaced piles will act as one large diameter pile, great, but they also are vulnerable to rotation. Whereas widely spaced piles more or less act as individual piles. This type of thing doesn't happen in static loading. Spacing means what happens if you look at Piglet or Randolph's work, what they say is that the amount of interaction between upslope and downslope piles will change. That's all that will happen. The whole mechanism doesn't change for them because the soil is never going soft. For us, the soil is kind of turning into mush, which means the failure mechanism can change. So this is the beauty of earthquakes and dynamics. We actually change the failure mechanism because the soil is able to. And you can't have the same for static cases. So getting the data plotting like this is one thing, but to delve more into it and get the essence of that out, for that we need to understand the failure mechanisms, and hence the title of the course. You cannot do this, you can't look at the dynamic loading on piles without knowing failure mechanisms. You can have a go, but you'll make quite big blunders if you do that. So this is the displacement for the large diameter and small diameter. You can see this one is trying to bend, whereas that whole thing simply rotated. So we did post-test site investigation to get the deformed shape as well. So we got data, we got the pre and post test configurations, and so we really need further guidance for piles in laterally spreading soil, especially when they're in pile groups. Spacing, I mean, we've done the two extreme spacing, right? Where does the bending translate into rotation? People can do more experiments between 5D and 2D, maybe 3D, 2.5D. We haven't done all that. You kind of pick the lowest hanging fruit and say, look, that is interesting, and move on to another problem. But to convert that into design guidance, I need more PhD students who can do those in between tests as well. And one of the problems in Cambridge is we are always having exciting new problems. We never go back and fill the gaps. Okay, that's all I wanted to say. Any questions you have? Yeah.
I'm very much curious to know how you are maintaining the density experimentally. How you are maintaining these less dense soil at the top and more dense at the bottom.
Like all these things, I spent way too long in the lab compared to my family when they were growing up, particularly. We built an automatic sand pourer which will actually pour the sand. You can bale, it basically controls the flow rate of sand and also the height of drop. Just like a 3D printer, it goes and pours the sand and you can choose the height of drop and the rate of flow of sand, and it will make dense and loose sands. So there's a machine to do that. It's like a 3D printer.
So you use the mesh, means different size of mesh for
Yeah, the hopper has a little wire mesh on it, and there are papers where we wrote about how do you calibrate it to get a particular density. But it's been in use for the last 20 years now. The current students simply know what they do calibration first in set volume cylinders, and they know exactly what density they'll get. And you weigh the model before and after, you know how much sand you poured, so you know the volume, you confirm you got the density as well. On top of that, these days we also push a in-flight CPT to confirm that the loose sand, where the dense sand is coming, where the increase in CPT resistance comes, all that is there. A lot happens. I'm not showing everything, otherwise I'll be here for 3 weeks. Even saturating the models with methyl cellulose, it's all a computer controlled process. There's a thing we developed called CAMSAT, so which keeps the flow rate small enough so that you don't fluidize the sand and slowly lets the fluid. It takes about 8 to 12 hours to saturate these models because you're trying to saturate them with 50, 100 centistoke fluid, right? So it's going to take a long time. When I was a student, we were doing it manually, and I would stay all night long in the lab. And I thought, this is ridiculous. So we built a machine that will do that. So, yeah, we improve slowly. Okay, anything else?
There is something called sharding effect file moves. So, how does that affect spacing? Sharding effect, like files in upslope and downslope.
Yeah,
Because of the files in downslope, there is effect on the downslope.
yeah.
So bending moment changes. I mean, like there is an effect. So, is there any effect in spacing?
Yeah, that's what we're talking about, right?
No, I mean, like, how does that affect?
Not as much as in the static loading. Because you're resetting the stiffness of the soil, in static, say, slope is there, and you apply lateral load, the upslope piles take a lot more load than the downslope piles because most of them are the ones which are opposing the movement, right? And that's what you're calling. This is all done by Randolph long time ago. What we have here is initially we thought that is what is going to happen, and then discovered actually no, because once the shaking starts, the soil stiffness is getting reset. So you don't get the same level of protection for the downslope pile. More than that, the global rotation mechanism taken over. So when we reduce the spacing, then because all the piles are connected through the pile cap, it's easy for it to rotate. And the whole bending moment has gone down in all piles. So that's why these liquefaction problems are interesting. You're starting with soil that is stiff and you're resetting. Yeah? Okay, anything else?